All right, here we go, folks. Ratios involving lengths and areas. In this video, we're going to be putting together some ideas from Unit 6 on similarity with what we learned in this unit on perimeter and area. All right, so without further ado, let's go ahead and jump right in. In number 1, it says we're starting with these two squares that have side lengths of 2 and 3. You know me, first thing I'm going to do is get a picture going so that I can get a visual of what we've got going on here. So here's my baby square with his little side lengths of 2, and then my larger square with his side lengths of 3. All right, let's get to the good stuff. In part A, they want us to explain why these two squares must be similar. I can think of a couple different ways right off the top of my head to answer this question, but I'm going to say that I can map one square onto the other using a sequence of similarity transformations, and that makes them similar. So if I were to say translate the little square onto the blue square using that vector, and then dilate using a scale factor of 3/2, the smaller one would be mapped onto the larger one using a sequence of similarity transformations, and that, folks, makes my squares similar. All right, so how would I phrase that in answer to question A? I'm going to say one can be mapped onto the other using a sequence of similarity transformations. Perfect. All right, what is the ratio of the corresponding sides? Well, side length of the little fella is 2, side length of the bigger guy is 3, so those numbers written as a ratio of the corresponding sides, bam, 2 to 3. Part C wants to know what is the ratio of their perimeters. Well, before I can compare their perimeters, I have to find their perimeters. So perimeter of the little one, 2 times 4 or 8. Perimeter of the bigger one is going to be 3 times 4 or 12. So when I compare their perimeters, 8 to 12, and simplifying that and into a fraction in simplest form gives me 2 to 3. Notice that the ratio of the perimeters is exactly the same as the ratio of their sides. And that's what this question is asking for us, or with us here. How does this ratio compare to the ratio of the sides? Well, the ratio of the perimeters is equal to the ratio of the sides. I'm going to use in this section a little shorthand notation. You're probably going to want to get on board with this too because it'll save you a little bit of writing. So I'm going to say RP for ratio of the perimeters is equal to RS, which stands for ratio of the sides. And in fact, not only the perimeters, but the ratio of any piece that's measured with length is always going to be equal to that ratio of the sides. That's kind of an important idea, so let's jot that down. The ratio of any pieces measured with length will always be equal to the ratio of the sides. So I'm thinking about what kinds of things might be measured with length. Altitude is measured with length. So if I were to compare the lengths of two altitudes, that would be equal to ratio of the sides. The lengths of medians measured in length. So when I compare the lengths of two medians, it's going to be the same as the ratio of the sides. Perimeter, of course, measured in length, ratio of the perimeters, that's why it's equal to the ratio of the sides. All right, so all of the ratios that we've looked at so far have been 2 to 3. Let's go ahead and tackle part D and examine what happens when we compare their areas. All right, area of the little guy is 4. Area of the larger one is 9. So when we go to compare those areas, 4 to 9, that, my friends, does not simplify down to 2 to 3. So the ratio of the areas is different, not the same as, a completely different number from the ratio of the sides, but they are connected. So how does this ratio compare to the ratio of the sides? Well, to get the ratio of the areas, I'm always going to take that ratio of the side lengths, square it, and that'll give me the ratio of the areas. So how am I going to write this using my little shorthand? Well, I'm going to say that my ratio of my areas is going to be the answer that I get when I take my ratio of my side lengths and square it. This too, have to know, it's a need to know. How do I remember? Well, area is always measured in square units. So to get from the ratio of the sides to the ratio of the areas, I'm going to square the ratio of the sides. All right, I know you're anxious to get into some problems and see how you might use this on a quiz or a test. So let's get down to business. In number 1, we've got triangle RST similar to triangle XYZ. They give us some side lengths. They also tell us some areas, and they want us to figure out, or they actually only tell us one area, and they want us to figure out the area of the second triangle. So I'm going to go ahead and draw me a couple of pictures. I've got this triangle RST. I've got a similar triangle, and remember when we draw these similar triangles, we want to match up these corresponding parts. So in the second triangle, R is going to match up with and correspond with S. No, I lied. R is going to match up and correspond with X. Let me go back and try that one more time here, folks. R matches up with and corresponds with X. S matches up with and corresponds with Y. And T matches up with and corresponds with Z. All right, took me a little bit to get it right, but it was worth it. Side length RS is 3 inches. Side length XY, 2 inches. Area of triangle RST is 27 square inches. Area of the smaller one is what we're trying to find. I'm going to call that X. Here's the piece that you're going to need to be careful of. When I find or compare the side lengths, I've got 3 to 2 or 2 to 3. Doesn't make a difference how you set that up as long as you're consistent when you use that ratio in your proportion. But if the comparison between the sides is 3 to 2, then the comparison between the areas has to be the square of that, or 9 to 4. When I go to set up my proportion involves areas. And because my proportion involves areas, I need to use that ratio that compares the areas. So when I compare the larger to the smaller, it's 9 to 4. Larger area in this case is 27. Smaller area is what we're looking for, or X. We're going to solve this proportion the same way we always have. Cross it up. So 9x equals 108. Dividing both sides by 9 tells us that the value of x is 12. X, remember, represented the area of our smaller triangle. So the area of triangle XYZ is going to be equal to 12 square inches. So the piece where you're going to have to be careful of these is that every problem now has two ratios, and you have to pick and choose accordingly and make sure you use the ratio that's appropriate for the problem that you are solving. In this case, we were solving a problem about area, so we needed to use that ratio of the areas, or the comparison of the areas. All right, let's take a look at the one more in the time that we have remaining. This one is dealing with pentagons. Again, it's telling us that they're similar. They are giving to us the ratio of their areas, and they're asking us to find the perimeter of the larger pentagon if we know the perimeter of the smaller one is 40 centimeters. All right, so I'm going to go ahead and set up a picture again. Pentagons are a little more challenging for me to draw than the triangles were. So I've got a larger pentagon and a smaller one. We're going to pretend like they look similar to each other. We know the perimeter of the smaller one is 40 centimeters. We're trying to find the perimeter of the larger one. I'm going to call it X. The other piece that we know here is that if we compare their areas, the ratio of those two areas is 144 to 25. I'm going to write this as a fraction rather than the colon. But when I compared those areas, I got 144 over 25. Keep in mind, perimeter measured in length. So the ratio that I need to use for this problem is the ratio of the sides. The ratio I have is the ratio of the areas. Keep in mind that the ratio of the areas is always equal to the ratio of the sides squared. So to get this ratio of the areas right here, we took the ratio of the sides and we squared it. So if we want to go backwards now, or unsquare that ratio of the sides, a nicer term or a mathematically correct term for unsquaring would be square root. So I'm going to square root the 144 in the numerator to get 12, square root the 25 in the denominator to get 5. So the ratio of my side lengths, or the ratio of any lengths, whether it's altitudes, medians, perimeters, that comparison between the lengths is always going to be 12 to 5. So that is the one that I'm going to use to find the ratio, or to find my missing perimeter. So 12 to 5 is the same as the comparison between 40 and X. Just like we did in Unit 6, make sure that when you set up those ratios, you're being consistent. I put the larger over the smaller in the first ratio, hence the larger perimeter over the smaller in the second. So when I go ahead and cross multiply here, 12x is going to be equal to 5 times 40. And actually, I'm going to go back because I just said be consistent, and I wasn't consistent, because notice that 40 is the perimeter of my smaller. So I need to get my eraser out here. I put the larger over the smaller in the first ratio. I have to put the larger perimeter over the smaller in my second also. So if you were sitting there watching at home going, what on earth is she doing, and why on earth is she setting it up like that, you were absolutely 100% spot on. I took a closer look at my work and then had to go back and revisit. All right, now I'm in good shape to go ahead and cross multiply. So 5 times x equals 12 times 40, or 480. When I divide both sides by 5, I find that the value of x is 96. So the perimeter of my larger pentagon is going to be 96 centimeters. Whew, that was a good one. I almost got tripped up at the end, but I fixed myself and got my course righted, so I'm feeling pretty good about this. All right, as always, thank you. Thank you for the gift of your time. Make sure you spend some time with those check your understanding questions so that you have your brain wrapped securely around this. And if you have questions, remember that I'm always happy to answer them the next time we meet again. All right, till then, take care.